So a unique feature of alkenes is the double bond. The double bond does not allow rotation. In other words, in an alkane, a single bond can rotate 360 degrees. A could switch with B and vice versa. At any given moment, A could be down here, B could be up here, through rotation of a bond in an alkane. However, in alkene, this A is fixed, this B is fixed, C and D. Okay, they're in fixed locations because the double bond does not spin. It cannot rotate like a propeller. Because of that, that creates a new class of isomer where the spatial arrangement is different. Those are called stereoisomers. To illustrate, this example, we've got 1, 2 carbons, 1, 2 carbons. Carbon 1, chlorine bonded to it. Carbon 2, fluorine bonded to it. Same. Carbon 1, chlorine, carbon 2, fluorine. So their connectivities are the same in the sense that you've got a chlorine bonded to one carbon and the fluorine bonded to the other. However, visually, you can see that these two molecules are different. Because that bond, there's no rotation, this fluorine in an alkene cannot flip up to be in this position. In this molecule, this fluorine cannot rotate down to be in that position. So these two molecules are different. They're isomers, they have the same chemical formula, but they have different spatial locations. And to denote that, I'm going to draw the implied hydrogen atoms. And when you have identical groups on the opposite side, like so, that is called a trans isomer. If identical groups are on the same side, it's called a cis isomer. Cis is on the same side. So I remembered it once upon a time. Trans is it's transverse, transported across, or however you want to remember it. But cis on the same side just always was something that helped me remember that. So these molecules are different from one another. They're not identical. They're related, that same chemical formula, the same connectivity, but the spatial location of the identical groups is different. Now, another example, just the requirement. This scenario, you have two identical groups on the same end. If you have this type of scenario, this is not going to be it's neither. You cannot call this either cis from trans. It's neither. And they're on the same end. Again, back to this template. here is an end. This way is a side. Okay, the end is 90 degrees from the side, or perpendicular to it. If they're on the same end, it's neither. Opposite sides, trans, same side, cis. And that's just the language that's associated when you have alkenes. You have the possibility for these three scenarios. Alkenes can undergo a major class of reaction called addition reactions. Where so-called because you add the chemicals listed above to the double bond. So just to draw an example, you can add hydrogen to that double bond like so. The double bond breaks and you create two carbon-hydrogen single bonds. You just added hydrogen to it. This is called hydrogenation. So if you look on the back of foodstuff or an ingredient that says partially hydrogenated vegetable oil, well, essentially this is what that's talking about. Take vegetable oil, bubble hydrogen gas through it, and you get rid of the double bonds that are in that vegetable oil to make a trans fat, potentially. We'll talk about that a little bit later. The next reaction's similar. Whoops. Instead of adding hydrogen atoms, you can add halides, like chlorine or bromine. And this is called halogenation. You're adding halogens. Again, an addition reaction. And these are called, collectively, symmetric additions. Because you're adding the same group to each side. The next couple are asymmetric additions. Next example, just going to draw it out a little further. It's called hydrohalogenation. You add in a hydrogen and a halogen, thing gives it away. And then lastly, adding water is called a hydration. Just like if you drink water when you're thirsty, you hydrate. Both of these reaction types are asymmetric additions. Because you're just adding two different groups to each side of that double bond. in this particular example, this carbon is bonded to 2 carbons. Carbon here is bonded to 2 carbons. So where the groups go is, the groups could go to either carbon because the carbons are equivalent. They're both secondary carbons. In the next slide, or the next part of the play posit, I'm going to describe the rules for how you predict what goes where when these are not equivalent carbons. The reaction above is a hydrohalogenation. HCl, hydrogen, and a halide were added to the double bond. You have 2 options. This carbon is bonded to 2 carbons. It is a secondary carbon. This carbon is bonded to 1 other carbon, so primary carbon. Or will become a primary carbon or a secondary carbon after the reaction takes place. So the rule is called Markovnikov's rule. Is that the hydrogen atom goes to the carbon with the most hydrogen atoms. As the major product. So if we look at this carbon, it's got 2 hydrogens bonded to it. This one has 1. In this product, the hydrogen went to where the other 2, to the carbon where there was the most hydrogen atoms. So 1, 2, 3. Look at the other possibility, 1, 2. The more favored product is this one. Because the hydrogen atoms went to, obeyed Markovnikov's rule. Now, why that is, when that double bond breaks, both atoms aren't added at the same time. They're added step 1, step 2. If the hydrogen goes to the carbon with the most hydrogen atoms on it, what that does is it creates a positive charge on this carbon, and the neighboring carbon helps stabilize that. And that positive charge is going to be attacked by the chlorine. It's beyond the scope of the course, that if you take a full-flown or full-fledged organic chemistry class, that would be discussed in greater detail, but for our purposes, the hydrogen atom that's added for the major product will go to the carbon with the most hydrogen atoms bonded to it. In other words, the hydrogen atom, the carbon hydrogen atom just gets richer.